Hi everyone, and thank you all for joining us today for the fourth in our series of webinars for 2019, which discuss LimitState software. My name is Tom Pritchard. I'll be introducing you to our speaker shortly and also rounding up at the end of the webinar. Today we're looking at modelling of retaining walls with LimitState GEO, and the session will provide you with an overview of how you can use LimitState GEO, which is our geotechnical stability analysis software, to rapidly determine the critical failure mechanism and margin of safety for a range of different geotechnical problems, ones that involve structures such as gravity walls, sheet pile walls, or anchored and prop sheet pile walls. The webinar is going to run for about 45 minutes in total and will include some time at the end for answering any questions that you may have. You can post these at any time using the question functionality that's present in the webinar interface on your screens. I'm aware we have a mixed audience today from right around the world, so some of you will be quite familiar with LimitState GEO and some of you may be quite new to it. We will try to answer as many questions as we can in the time that we have available, but given numbers it might not actually be possible. So apologies if we're unable to get round to yours, but we will always ensure that we reply to everyone via email in the days following the presentation. So, without any further delay, our speaker today is Dr. Colin Smith, who's the LimitState GEO Product Manager, and I'll pass you over to him.
Okay, thank you very much, Tom. Get these slides working. Okay, so just to whet your appetite, kick off with a slide showing a selection of problem types that can be solved by LimitState GEO. And we'll be discussing some of these later in the webinar, but as you can see, the software can model footings, retaining walls, slopes, or a combination of those. So in terms of our contents, we're going to be looking at how LimitState GEO can be used to solve retaining wall problems, how that differs from other methods, and how to model a number of specific scenarios. As it's a problem-specific webinar, I'm going to focus on how the software can be used to solve retaining wall problems, so I might skip over some of the details of how to use the software, but hopefully the process should be clear. To this end, I'll be using the software directly to illustrate the key points, but we'll have a few slides at the beginning and end for an introduction and summary. And as this is a short presentation, the main aim is to give you a flavour of what the software can do, and there won't be too much time, unfortunately, to get into the details of all the functionality. However, as Tom said, there will be time at the end for questions. Before we look at the software itself, I'll give you a little background to LimitState. Our mission is to provide engineers with powerful software for ultimate limit state analysis and design, leveraging the latest state-of-the-art algorithms on optimization technology. And this innovative approach has generated a client base spanning over 30 countries worldwide. So where does this software fit? Well, we focus on tools for ultimate limit state analysis, and this really allows us to provide products that combine the speed, ease of use and simplicity of traditional methods, but give us all the flexibility of finite element type methods to handle any problem geometry. Because we're focusing on ultimate limit state, the only parameters we require are generally cohesion, friction and unit weight of our materials, and a few other properties for particular special cases. So that's a very quick introduction. Let's try out the software and look at retaining wall analysis. So, if we first think about classic approaches to retaining wall analysis, we can see a broad consensus on general principles of how that's done, and those that generally get adapted for specific scenarios. So typically a limit equilibrium approach is used, and we might use a Rankine earth pressure type approach, or a Coulomb wedge type approach. And LimitState GEO essentially is like an enhanced wedge analysis, where it's able to model not just one single wedge or two wedges, as you might do in a hand calculation, but it can essentially model hundreds or thousands of wedges and give a very accurate result. So, we'll look at a few other examples. So this can be used for a whole range of retaining wall type problems. So here you can see cantilever walls, anchored walls. We can model bending failure in walls and propped walls, and a whole range of other problems in between. terms of how that compares to other geotechnical analysis software, showed you this slide before, so just to recap, it gives us that flexibility of the finite element approach, simplicity of the traditional methods, and how it does that is based behind the analysis method that it adopts. So it uses a technology called discontinuity layout optimization, which provides rigorous upper bound plasticity solutions. It's a rapid and direct way of going straight to the collapse state without having to increment towards that. Came out of a research project at the University of Sheffield, and the original work on this was published in 2007 in the Proceedings of the Royal Society, and there have been a number of subsequent publications since then. To explain how it works, which hopefully knowing how it works will give you an insight as to how to best use the software. We'll take a very simple problem here. We've got a block of soil, rectangular block of soil, fixed on the left-hand side of the base with a surcharge on the surface. To solve the problem, we discretize the problem by putting a series of nodes on the problem rather than elements, so it's a node-based problem rather than an element-based solution. And so here we put a very small number of nodes, just 12, 3 by 4. What we do is, in effect, we connect every node to every other node with a potential slip line. So that gives us, from our 12 lines, 12 times 11 over 2, 66 possible slip lines. And then we use optimization to search through all those possible slip lines and find the set that gives us the failure mechanism that dissipates the least energy. And that's going to be the critical failure mechanism. And in this case, there are 6 slip lines that combine to give the critical mechanism. Now, that's a very simple problem. Generally, we're going to solve problems with 500 or 1,000 nodes, which can deal with millions of potential slip lines and billions of potential combinations of those slip lines to give us mechanisms. So essentially, the more nodes we have and the more potential slip lines, the more scope the software has to determine a failure mechanism. So this slide illustrates the process in a bit more detail. Those initial nodes you can see, we've got several hundred on the domain appeared here. Software then finds the optimal layout of slip lines, and then once it's done that, it puts those together to form blocks and animates that simply to help interpretation, so you can see how the failure mechanism is developing. And as I said before, if you put more nodes in the problem, then you should be able to find a more precise mechanism. Now, of course, you want to be sure that this software actually achieves accurate results, so we have verified it against a wide range of closed-form solutions and benchmarks in the literature. Every time the software is modified, it runs hundreds and hundreds of tests to make sure that it's still doing the same thing. We've put about 100 of those up on the website, so you can view a whole range of problem types, from foundations to slopes to anchors to retaining walls, and look at the accuracy that's achieved. So what we've got up on here is an undrained anchor problem, and the software is getting to within 0.7% of the benchmark result in the literature. In terms of retaining walls, we have just produced a few little graphs here, very straightforwardly looking at smooth and rough retaining walls and active and passive earth pressures. The red line in the graph on the right is the theoretical result, and the blue dots are the results from the software, and as you can see, that fits pretty well exactly. And the same for the passive case, exact fit for both smooth and rough retaining walls. Of course, the smooth calculation is quite straightforward. That to do analytically, to do a fully rough condition is a little more complicated, but the software deals with that with ease. And then finally, a lot of academic literature has been written using the software, both in terms of the how to use it, using it for specific problems, and developing the technology underneath it. And those we put together a bibliography which you can find on the website, which lists all those papers. Okay, so that's enough introduction. Let's move on to gravity wall analysis, which also encompasses gabion walls. So in terms of analysis, conventionally we're going to you do a number of calculations to establish whether the wall is stable against sliding failure, overturning failure, bearing failure, and generally also look at a global failure that would go around the wall. So essentially we're checking 3 or 4 failure modes out of essentially an infinite number of possibilities. With LimitState GEO, there's no need to do those separate checks. The software will find the critical mechanism out of all the possible failure modes, which includes those 3 classic ones that are assessed, and it will then give you the margin of safety for that particular result. Before we go to look at models, I just want to say what do we mean by an ultimate limit state analysis. So essentially anything we design should be stable and nowhere near its limit state, its ultimate limit state. So in order to do an ultimate limit state analysis, we have to drive the system to collapse by some means. And we can do this implicitly or explicitly. In many conventional analyses, the process is typically implicit, i.e. you don't sort of see that directly, but it's implicit in the calculations. In general, with numerical analysis, we've got to do it explicitly. So we've got 2 possible ways of doing that. One is a factor load approach. The simple question is, how much bigger does a load need to be to cause collapse? So by what factor A does the load need to be increased to cause collapse? So here we have a surcharge on the surface of the soil behind a retaining wall. By how much do we have to increase that surcharge to get collapse? That's the sort of question we're going to ask. And that's our factor of safety on load, that particular load, and in the software we call that the adequacy factor on load. And we can apply that to surface surcharge. We could also apply that to the weight of the soil behind the wall. The second approach is a factor strength approach, which is basically asking the question, how much do we have to reduce the strength of the soil by in order that collapse begins? And that gives a factor of safety on strength. And both have their advantages and disadvantages. It depends on the type of question you're asking in terms of your stability analysis. So the software will output a thing that's called the adequacy factor. We'll see that in a moment. Generally, if the factor is bigger than 1, it means we've had to increase a load or decrease a strength to get to failure, so the problem is stable. If the number's less than 1, then it's unstable. And generally, if we're doing factor load type approach, we should apply it to an unfavourable load in the system. And if we've already applied partial factors, then this number will give us a measure of the over-design over and above those partial factors that have already been applied. So we'll move on to a demonstration and go through that. So we're going to look at a gravity wall problem and assess that against sliding. So this is the software. Let me just fix that in place. So we've got a gravity wall here with some soil behind it. This is the general layout of the software. So we have a number of buttons along the top and the side to control. Down the side, that's generally to control the geometry, standard sort of buttons up here to look at different properties of the problem, and then we have a property editor on the right. Essentially anything we click on the problem, such as this wall, its properties appear here, and we can interrogate those values and adjust them as required, and I'll illustrate that as we go along. We also have what we call a materials explorer here, so we have a number of materials. For this problem I've pre-specified the material for the soil behind the wall and the wall itself, and the interface between the wall and the soil, and then we have some built-in standard materials which you can use to put together a model quickly, just to get a feel for any particular type of problem. But you can define material properties, any values that you like within the software. And then finally down here we have what's called the geometry editor. So again, if I click on the body, it will give me the coordinates there, and I can edit any of those values if I wish to change the geometry. So, looking at this problem, the soil here, I'll just say no to that. The if I look at the soil here, this block here has certain properties which I will just look at later on, but it contains a soil here. We've got a cohesion of 0, angular friction of 38, a unit weight of 18, and we're told the soil behaves in an always drained manner, so it's always going to use the effective stress parameters in the analysis. The material down here is a dense sand, so it's sitting on a very strong base, and we can also define interface properties. So if we click here, the interface between the wall and the soil also has properties, and here we've defined it that we have a cohesion of 0, a C-dash cohesion intercept of 0, and an angular friction of 25. So that's less than the soil there. Final thing is we're going to look at sliding failure. I'm going to do a factor load analysis first, so I have a setting here where I adjust that, and what I'm going to do is basically ask the software how much heavier does this body of soil have to be to cause collapse. And you can see that there's this property called adequacy true, and that means that we're telling the software you increase that value of its weight until we get to collapse. And then I click solve, and we get a very simple single wedge analysis. So sometimes they are quite simple, and we've got a factor of 2.373. If I click on that value, it will just explain what that means. It's basically saying the problem is stable. We have to increase the unit weight of the object S2. If I click on that, just click on that, that tells me what the object is. So basically all the soil there has to have a weight 2.3 times bigger than it actually has. So it starts with a weight of 18. To actually get collapse, it would have to weigh 42 kilonewtons per meter cubed. So that's essentially what the analysis is telling me, and if I click this button here, this is animate, it shows me what's going on. So we get sliding of the wall on the base soil. Now, I may be more interested in actually what is a margin of safety I have on the strength of the soil here, so I can go for factor strength, and in this case what the software does is it reduces the strength of the materials until we get collapse again. It takes slightly longer to do this, it has to iterate a little bit more than for the previous solution. And in this case, it's telling me that the soil has to reduce its strength by a factor of 1.3, so these are the characteristic values, these are actually the values of the soil properties that would have to be present for collapse to occur. And in this case, you can see that actually we've got a little bit of base failure as well as so it's almost sliding, but the wall is starting to tip forwards due to that base failure at that particular point. But the number is still bigger than 1, so that means that it is stable. And if I put that back, I can also, if I click on here, I can see the pressure distribution, so we can look at, we get a little histogram of pressures, and average stresses are displayed as we go down. So these increase with depth, as you'd expect, typical sort of active pressure distributions. Now, if I wanted to do a Eurocode type analysis, I can click here and use what's called the scenario manager, and this applies partial factors to our parameters. So at the moment we're using unit factors on everything, but I can select, for example, design approach 1 combination 2, and that will then start applying factors of 1.3 to any variable and favourable loads, which we don't have in this problem, and in particular factors on the material properties. So again, if I run that solution as a factor strength mode, then I get a solution of 1.076, so it's still bigger than 1, but that means I've only got about 7 or 8% additional margin of safety over and above the Eurocode factors, but that's still adequate. We've effectively satisfied the Eurocode, or we complied with the code there. Now, in order to apply the Eurocode, the software needs to know which materials or properties are favourable or unfavourable. So if I click on the body of soil here, its weight is going to be unfavourable. It's actually been set as neutral here, and neutral in the software doesn't have a strict Eurocode definition, it just means don't apply any factors. Strictly we'd set that to unfavourable. In fact, it doesn't make any difference for design approach 1 combination 2 because permanent unfavourable loads get factored by 1 anyway, so we would get exactly the same result. And we could revert back to factor load and see what happens with those Eurocode factors applied, and we don't get such a big margin of safety, and we start to see a slightly different failure mode because we've reduced the strength of the base material. So we do get that type of problem. So that's generally a sliding failure. We've seen a little bit of overturning. If the base material was weaker, then we'd see more of that occurring and more kind of base failure. So we get a larger failure mode and a bit more turning. So that covers a brief introduction to gravity walls, and we can also analyse gabion walls, which are effectively, we build a gravity wall out of blocks or gabions of soil, a bit like a large masonry wall, but then the interlocking of the blocks themselves can fail on their interfaces, so that's another feature that can be modelled. What I'm going to do now, rather than look at the gabions, is just go back to the slides, and we will just remove that. Just say a little bit about ultimate limit state analysis. So the software is based on the theorem of plasticity. It employs a rigid plastic model within a limit analysis framework to generate those ultimate limit state solutions. So we need to be careful in modelling brittle materials, i.e. materials that display a peak strength. And generally the simplest option is to use the critical state strength that we can rely on at all strain levels, and that will give us generally a safe result. A lot of debate about using peak strengths, but the simplest solution is to use the critical state strength. We're now going to look at some cantilever walls and anchored and propped sheet pile walls. So conventionally, when we analyse that, we assume a Rankine earth pressure distribution, and we assume moment and horizontal equilibrium, and we can assess the stability of a wall, a cantilever wall, and determine a point of rotation. And our typical design questions might be: how long do we want the wall to be stable, and what's the maximum bending moment likely to be in that wall? So we'll have a look at how we can deal with that in the software. Let's see if I bring up the cantilever wall example. So here I've modelled a cantilever wall. I've actually modelled it as a thin rectangular block of material here, which is called a wall, but is actually a rigid material, so that means it cannot fail under any circumstances. But it can have a weight, so it has a weight of 24 kilonewtons per metre cubed. So there I'm representing effectively a concrete wall, reinforced concrete wall. We're modelling around that basically a loose sand with an angle of friction of 30 degrees, and we have a surcharge load up here of it's a variable load of 5 kilonewtons per metre cubed squared, and we've got adequacy true on that. So essentially, if we're going to do a factor load type analysis, we're going to ask software how much bigger does that surcharge on the surface have to be to cause collapse. And that might be a question we want to ask, what's a safe amount of surcharge or additional material we can put on the surface before this thing fails. So again, we make sure we've got factor load there, click solve. It finds our mechanism, we can animate that. So we get get a returning result, and I get a factor of 6.37. So that's basically saying that surcharge has to go up to 30 kilonewtons per meter squared before this wall is going to fail at that kind of embedment. So essentially the wall is over-designed for the current surcharge. If we wanted it to be just on the point of failure for that surcharge of 5, then we can make the wall longer or shorter to get there. Now if I click on that, I can see its y coordinates are here. Just to save time, rather than typing in a range of values, I know in advance of that if I move the base of the wall up to coordinate 0.43 to that position, if I click here I can get a view of the whole problem again. If I analyse that problem, then I get a factor slightly bigger than 1 actually, but we're getting closer to that, so a little bit shorter, and then we'd have a length that was just on the point of collapse. And if we'd been already applying, for example, Eurocode partial factors, then that's what we'd be looking for. And if I click on this wall here, just say yes to that, then I can also see the distribution of pressures on each side. So essentially we're getting active earth pressures down here, and then it goes passive right at the bottom, where this end of the wall is actually moving backwards rather than forwards. And the same here, we're getting passive pressures down here, and then towards the base it doesn't increase quite so much due to that rotation of the wall. Now that allows us to vary the wall depth. We can also, if I just shut that one down, as well as using a block of rigid material to represent the wall, I can use what's called an engineered element in the software. So here's a similar model. I just zoom in on it. Same, slightly different soil, soil A, put a 40-degree soil on that. And this time the sheet pile here is made of what's called an engineered element. And if I look at its properties, sheet pile here, I have a number of parameters here. Now these engineered elements can be used to model things like soil reinforcement, geotextiles, soil nails. So I have a number of additional properties that allow that flexibility to model a whole range of different geotechnical structures or materials that we use in geotechnical construction. So we don't need to worry too much about those. Essentially we have a thing called a pull-out factor and a lateral factor. These are more related to soil nails that we effectively, for sheet pile walls, we just set those to what is essentially infinity 1E30. We also have the ability for the material to fail in tension and compression. Again, we're not really usually worried about that, so I've set those to infinity. But we also can set a moment of resistance, which allows failure by bending of the wall. So currently we're set at 150 kilonewtons per meter squared, or sorry, kilonewtons per meter, kilonewton meters per meter. So that's the sheet pile, and we can view its properties here, or as I said, that it's also available over here, sheet pile. If I click on that, I get exactly the same properties there. If I click on here, you'll see that we've got this engineered element is in the middle, but on the right and the left hand side we can also put interface materials. So if we look at the right hand side, effectively I've put a frictionless interface on, that's just got 0 shear strength, and I've also put what's called a tension cutoff. And that basically says that the interface can take any amount of positive compressive stress, but as soon as the stress goes negative, a gap will form. So that allows the formation of tension cracks. So essentially I've got a limiting stress here, a compressive stress of infinity, and here a limiting tensile stress of 0. Anything I click on here, it's a little explanation appears down here in this box, and often there's a hyperlink to the manual. So if you want to just explore the software and try to work out what these things do, you can find a brief explanation here, and then you can go straight to the manual for a bit more information. So I'm going to do a factor load analysis, and what I've done is essentially I've set the soil behind the wall as adequacy true, so I'm asking the software how much more does this soil have to weigh to cause collapse. So I click solve and get a very simple wedge type mechanism, which I'm expecting because I've got a smooth wall. The wall just fails by rotating that way, and one of the nice features of the engineered element is that it will now give me it can give me plots of axial force, shear force, or bending moment in that element, and in this particular case I'm most interested in the bending moment, so this is the distribution of bending moment that I get down the wall at ultimate limit state. And I've got an adequacy factor down here about 1, so that actually means that this system is on the point of failure. And because I've got a factor of 1, that means I haven't really changed the weight of the soil behind this. And so this bending moment distribution is valid. Had this number been much bigger, then I wouldn't really have had a realistic weight of soil. So generally we're looking for results where we get our adequacy equal to 1, or we're doing a factor of strength analysis. So we see this wall failed by rigid rotation. We can actually just demonstrate a bending failure. So if I change its strength here, for example, I'm going to put a very low strength in here, 15 is its bending strength, and then rerun the analysis. What happens is the software decides that it's actually easier, rather than causing the whole thing to rotate, to actually hinge about this point here and have a reduced failure. And then you can see that the bending moment at that point has reached a value of 15. And then finally, just to show that we can model, for example, tension cracks, this soil here currently has a cohesion intercept of 0. I'm going to set that to 5, so that will allow it to effectively stand up at a vertical face for a short depth. And if I rerun the solution and I animate that, you can see that a gap is forming between the soil and the wall, and so it is able to model a tension crack and get that correct, and you can see the bending moments effectively stop at the base of the tension crack, because above there's no more lateral force on the wall. Okay, so hopefully that's demonstrated how we can model cantilever walls. I'll just quickly go back to the PowerPoint. So just to kind of summarise the points I was making there, if the adequacy factor on the load is bigger than 1, then we have to remember that any derived bending moments or pressure distributions relate to the problem analysed with the non-unit adequacy factor applied. So those pressures or moments that we derive correspond to that factored soil weight. Now in conventional design calculations, we're generally designing to an implicit adequacy factor of 1, so this issue doesn't arise. So essentially, to avoid this, we need to use a method that gives us an adequacy factor on any load of 1. So we can either change the wall length until we get an adequacy factor of 1, that will perhaps give us our optimal design of wall. We can reduce the bending strength of the wall until we get bending failure, an adequacy factor of 1, or we can use a factor of strength calculation, and then our results will be similar to a mobilized strength type approach, which will typically give us a somewhat higher bending moment. But that's just something to bear in mind with this type of analysis. You have to keep in mind what the results and the parameters that have been produced, where they're coming from. And just one final note, because this is doing a rigid plastic analysis, we're assuming full soil strength and mobilised simultaneously on both sides of the wall at failure. In practice, that might not be the case. And we might find that as you would get in conventional limit equilibrium analysis, that a serviceability limit state bending moment distribution might be larger than what you get from an ultimate limit state, simply because the pressures are going to be larger at serviceability limit state. So just one other factor to be aware of or to remember. Okay, so we're going to wrap up by briefly looking at prop wall analysis. Key issue here is how do we model the prop and work out what the load in the prop is, and an anchored wall analysis. How do we model an anchor? How do we work out the force in the anchor tendon, and how do we look at the interaction of those two? So I'm going to go through those fairly quickly as we're coming to the end of the webinar. So just pull up wall. So the key thing is here how we model this interface, and essentially if I click on the interface there, so I click on the prop first. The prop is just modelled as a rigid block, and we've modelled it with a fixed boundary here, so it's basically just a bar sticking horizontally. It touches the wall here, and the key thing is that on the left hand side we have this tension cut-off material, and as I said earlier, that allows a tension crack to form between soil and wall, but it also allows the wall to pivot on this rigid prop. So if I do the analysis in this particular case, and of course we get a slightly different mechanism. It's not this classic wedge mechanism that is assumed normally because we're pivoting about the top of the wall here. But if I animate that and zoom in, it's not so easy to see here, but essentially this wall is basically pivoting at the bottom corner of this rigid block, and that allows it to freely pivot at that particular point. If I click on this block, anything I click on any block after we've done the analysis, I can see the forces acting on it. So at this end, it tells me what the stress is that is acting on that, and from that I can determine what the prop force is in the problem. So that's very briefly looking at a prop wall, and then finally we'll look at this anchored wall. I'll first just solve that, show you the sort of failure mode. So here we're modelling failure of the wall, which is rotating about its the anchor tendon point, but that in turn is moving slightly forward, so the tendon is pulling on this anchor and causing failure. So in this case we've got simultaneous failure of the anchor and the wall. Now the key thing about this is that this anchor tendon we're just modelling is something that doesn't interact with soil, so we're using again an engineered element, but this time we set all the parameters to 0 apart from its tensile strength, which we can set to some value, but all these numbers effectively say how does it interact with the soil, and we're saying it doesn't interact at all. And if we zoom in very closely, we can see that the wall, well, we basically model the wall and the anchor plate, this Deadman anchor, as an engineered element with in the same way as we did with a cantilever wall. And what you can see, we've also included a little T-bar here to connect to the anchor tendon. And the reason for that is that where two engineered elements meet at any point, their bending strength is a minimum of the different engineered elements. So if we connect the anchor tendon, which we've told there's no bending strength to this, directly into the anchor plate or into the wall, then it will introduce effectively a frictionless hinge at that point, which will not give us great stability. Now, when we looked at this particular analysis, what we saw was that the failure mechanism behind the anchor, or behind the wall, and the anchor itself, they don't interact. And of course we know that there's a distance, an optimal distance to separate the anchor and the wall before those mechanisms interact, and then we get less benefit from our anchor. So we can play around with that and move these together. And the way to do that is I can click on the anchor plate and it's connecting the block, and then I can just drag that sideways. So I'm going to move it fairly close, about there. And then when I solve, we can now see that we get a very different mechanism. The anchor is now too close to the wall, and actually it just turns it into a sort of rigid block of soil between the anchor plate and the wall that slides, and we get a lower stability. So we have a factor here of 0.52, whereas before it was about 0.96, so we've lost a lot of stability there. So it means you can play around with moving the anchor, or you can change the wall length and do kind of what-if type calculations, how to model those. Okay, so we're getting pretty close to the end of the webinar, so I've very briefly looked at those two problems, but happy to take any further questions on those. So just to wrap up with some conclusions. So hopefully we've shown that the analysis that we undertake here uses similar principles and mechanics as conventional limit equilibrium methods, but it can handle much more complex geometries and kinematics. We don't need to consider separately different failure modes, such as sliding or toppling. The software will automatically consider all of those simultaneously and find the critical one. And we can handle a whole range of different features, such as variable surface loads, variable backfill geometry, including slopes. We can model tension cracks, wall interface properties, layered soils. Haven't had time to look at water, but we can put water into the problems as well. So you've got the flexibility to use the software to model any degree of complexity that you like, and hopefully you've seen that. Sorry, go through those. That it's very interactive software. It's solved very quickly, so you can use it to answer those what-if type questions, get a better feel for the problem, and look at more complicated problems where your retaining wall might be on a slope and you're wondering how those things interact. There's no need to impose idealizations or correction factors for non-standard geometries, and no need to try many different programs to solve different problem types. So we'll finish there and we've got time, a few minutes for questions. Okay, so we've got a question on the gabion walls. So I mentioned those very briefly, and we'll just jump back to get the software up. So if we just run the software as is, one thing I didn't demonstrate is that we have a wizard which allows you to quickly build standard typical geotechnical constructions. And those range from foundations to gravity walls and so on. And in this particular case, there's one for a gabion wall, so we'll click on that. We can enter some general properties about the project, but really we're interested in the geometry, and this allows us to build quite quickly a set of gabions at a particular angle with certain soil properties. I'm going to keep with most of the defaults here, but I'm going to change this height of layer A to 7 meters, or thickness rather, this width here. Change its width to 8, and I'm going to model. Okay, stick with that, and then I'm going to model 6 gabions, but I'm going to stick with the other defaults. Now we can have the gabions aligned with the left or the centre or the right, but I'm going to stick with the left at the moment. And I'm going to keep the default material properties, default surcharge, and just for simplicity, I'm going to keep that, make that a coarse nodal distribution, and click finish. So it's basically built me a gabion wall model. I've got those 6 gabion walls, and effectively the gabion is modelled a bit like a block of masonry. It essentially has a rigid centre to it, but it's the interfaces that are really where the modelling takes place. So if I click on an interface there, I've actually got two materials. I've got what's called the gabion frictional interface, so I can set the frictional or cohesive interface properties which allow those blocks to slide. But I've also got, using a cutoff material, that means that the blocks can rock. But also what we know is that gabions quite often can crush, particularly at the corners. So by putting a non-infinite compressive strength, we can represent that kind of squashing of the corners at the of the blocks if that is likely to occur. So if I click solve on this, I get a failure mechanism, and basically the whole set of gabions behaves like one monolithic gravity wall. But we can show that you can actually fail between the walls. So what I'm going to do is change this material property B. I'm going to give it a very high strength, and we're actually modelling this as an undrained material. I'm going to give it a strength of 500. So basically that bottom block is locked into the lower soil, and when I fail, then the software says, it's too much work to slide along there. I'm going to fail through that upper interface, and we can repeat that process as we go through, and if I change the geometry of the gabions, we could also get toppling type failure for that. Okay, so that's covered that. I've got probably time for one more question. So the question is, I'm just reading it here. Okay, so if we go back, it's a question about the Deadman anchor problem. So the question was, why have I got these lines here? So essentially the software, when we draw bodies in the software, they have to be in interconnecting blocks, so we can't just have a line which has got free ends. Basically we have to have distinct blocks of material for the software to be able to solve the problem, and we can't just have a free end of a single line. So these have to appear somewhere. Now they don't actually have to be horizontal, they could be angled, or they could be connected to the top of the line. So if I go from here to here, I could have connected that there, and then I should be able to delete that one. So I can do that in any way I like. It's simply that we just cannot have effectively lines floating with free ends in the problem, and it's just necessary to put those lines in. It shouldn't really affect the analysis in any great detail. It will slightly affect the distribution of nodes. If I do this analysis preview nodes, it shows me where all the nodes are going to go. So it's slightly different offset of nodes in this area than in here, and there's also nodes along these boundary lines. But generally, if you take the default settings in the software, it doesn't make a significant difference to the analysis. So the main reason in that particular problem that I set them the way they were, and if I just click this undo button, I can go back to where I was. I'll just unlock that, so revert back to where I was simply that when I demonstrated that dragging of the line of those, it just keeps things tidy because they then just move horizontally, and we don't start getting significantly angled lines. But that's purely the reason for that. It wouldn't really have made any difference if these had been located elsewhere. So in terms of guidance, I think it's whatever keeps the geometry tidy. The analysis shouldn't really be affected by where they are, as long as you've got the same number of nodes distribution in adjacent blocks, and typically we recommend having twice the nodal density on lines, but they are set by default. Okay, well, we've come to the end of the webinar there. If there are any other questions, we will answer those by email, but I'll hand back to my colleague Tom just to wrap up. But thank you very much for listening, and hope you found that useful.
Thanks, Colin, and as Colin said, thanks everybody for listening today. I do hope you found that the webinar was informative. Maybe you learned something new about the software. As we mentioned at the start, if it has prompted any questions, then you can get in touch via telephone or by emailing us at support@LimitState.com, and we'll be happy to speak to you about it. If you'd like to watch the webinar again, or if there are people, maybe a colleague who you think might be interested to see it, we'll make a recording available later today or early tomorrow, and we will also email you with a link once it's available online on our YouTube channel. Finally, also please look out for our other webinars which deal with LimitState GEO. They'll be taking place throughout the year, and we'll be sending out event notifications via email and also posting on social media in advance of these. They'll be on our website at LimitState.com/webinars. So lastly, I'd just like to thank you all again for listening, and hope that you can join us again for one of the future sessions. Goodbye.